All right, in this video, we study how to integrate some functions by changing variables so that the computing the integral becomes easier. So let's start. First of all, what do we mean by change of variables in this case? For that, let's consider two-dimensional spaces. Okay, so u and v and x and y. Okay, and we consider a map from UV space to XY space. Okay, and let's call that map phi, capital phi. Okay, so capital phi of U and V is equal to X U and V and Y of U and V. So that means X and Y are both functions of U and V. By this transformation or map, suppose we have a bounded closed region E in the UV space. By this transformation, this bounded closed region is mapped to some bounded closed region D in the XY space. I mean, we are assuming this phi is a continuous map, okay? This must be continuous. Otherwise, a bounded closed region may not be mapped to a bounded closed region. But if we assume the continuity, then it is the case. Is the image of E by the map phi is D. Okay? Furthermore, we require this map to be injective. Injective. That means two different points in E are mapped to two different points in D. Okay, so it does not happen that two different points in E map to the same point in D. Okay, that doesn't happen. And also, we require that the Jacobian, the determinant of the Jacobian of this phi is non-zero at everywhere in E. Okay, so that means the Jacobian determinant is this. Dx du, dx dv, dy du, and dy dv. So at every point in E, this is non-zero. So if we calculate this determinant explicitly, that is this times this, dx du times dy dv minus dx dv times dy du. So this is non-zero. Now, if we have a function f of x and y, which is continuous function, continuous on the region D, then we can compose f and phi. So f after phi uv is this, f of x of u and v and y of u and v. So this is a composed function. Okay, so how can we use all these to calculate a multiple integral like this one, dx dy? First of all, this is not equal to this, x u o v and y u v and du dv. To see why this is wrong, let's consider the simplest transformation between uv and xy. For example, phi of uv is equal to constant times u and constant times v. Okay, So that means x is equal to cu and y is equal to cv. So this is a simple linear transformation, and c is non-zero. It's just a constant. So in that case, if we draw the region here, u and v, if this is a rectangle in UV space, the image of this E becomes also a rectangle in XY space. Okay, so this E, this rectangle E and this rectangle D, they are similar, but scaled by C, right? So that means if we move one unit in, so one unit of area in E corresponds to one unit of area in D, but their sizes are different. But this one cannot be equal to this one. So this f is not scaled, but this dx, dy, and du, dv, they are scaled. So they cannot be equal. So how can we make them equal? In this particular case, if we, since we know x and y are given by this, so dx is c times du and dy is equal to c times dv. So it makes sense to change the variables in this way. So dx dy is equal to c squared dv, du dv. So this integral, so if we replace dx dy by this, then it should be that instead of du dv directly, we should have c squared du dv. So then it is, they are equal. So what was missing was this term, this factor. Okay, so this is the case when we have this mapping. Okay, so in general, it is not this, but what is it then? In general, this map phi is more complicated. It can be any continuous map. So in that case, we have the following: xy dx dy is equal to the integral on E x of u v and y of u v, and the absolute value j u v and du dv, where j is the determinant of the Jacobian. So that is dx du and dy dv minus dx dv times dy du. Okay, so we take the absolute value of this, and that is this one. So instead of c squared in the previous case, in general, it becomes the absolute value of the Jacobian. So this is actually a theorem that should be proved, but the proof is a bit too complicated, so I will skip it. Instead, I will try to explain the intuitive meaning of this equality. To understand the meaning of this equation, we go back to the definition of the multiple integral. So what we are doing is to integrate a function on some region D. Okay, so this is xy space, and we define a map phi that maps a rectangular region E or some simpler region, rectangular region E to some arbitrary region D. So first of all, we partition this rectangular region E into small pieces. Okay, so let's see, 1, 2, 3. So this partition is mapped to region D like this, and so it may look like this. And what's important is we are assuming that this map phi is continuous and injective. Okay, so that means if we pick any one piece from E, then that is mapped to, there is a corresponding region in D, and the neighbor of this region, like these yellow ones, are also neighbors of the corresponding region in D. Okay, so neighbors are mapped to neighbors. So that's what's important for, it's an important property of continuous map. And also, we're assuming it's injective, so there will be no overlap of neighbors in the region D. Okay, so two separate neighbors do not overlap in the XY space. Okay, so let's assume that in this UV region, this is A, and this is B, this is C, and this is D. And as usual, we label these grids as A0, A1, and so on, and up to AN. And this is C0, and this is C1, and so on, and up to CM. Okay, and let's label this as EIJ. So this is AI, and AI plus 1, and this is CJ, and CJ plus 1. Okay, and the corresponding region in XY space, let's name it DIJ. So EIJ is mapped to DIJ. Okay, now let's focus on this region and this region. Okay, so this would be EIJ, and this coordinate here is AI and CJ. This coordinate here is AI plus 1 and CJ, and this coordinate is AI and CJ plus 1, and this coordinate is AI plus 1 and CJ plus 1. Okay. And the corresponding region DIJ, it looks like something like this, and it is of course closed and bounded. And so this is an this has an xy coordinate. So this coordinate is x of a AI CJ. So this point is mapped to this point. Well, actually, it depends on the map phi. So this point may map to this point, or this point, or this point. But for the sake of explanation, let's assume that this point is mapped to this point. Okay, and same for this one. X and Y is AI AICJ. At this point, we have X of AI plus 1 and CJ, and Y of AI plus 1 and CJ. And same for this one. And X AI CJ plus 1 and Y AI CJ plus 1. this one, x a I plus 1, c j plus 1, and y a I plus 1, c j plus 1. Now the area of this eij, so we write area by represent the area by this function mu. The area of eij is this length times this length, right? So that is ai plus 1 minus ai times cj plus 1 minus cj. And what's the area of dij? Okay, that is not straightforward, but we make some approximation to make things easier. So first we uh, consider this parallelogram connecting these points. Okay, so this and this, there are two vectors, and we make a parallelogram using these two vectors. Okay. So this and this are parallel, and this vector and this vector, they are parallel. So we approximate the area of dij by the area of this parallelogram. So the x component of this vector is this, and the y component of the same vector is this. And we do a similar thing for this vector. And for that, let's use blue here. We take the difference between this and this, so that is x ai cj plus 1 minus x. So this is x coordinates, ai and cj. So this is approximated as, so the difference is only in this coordinate, so it's dx dv cj times the difference here, cj plus 1 minus cj. And for the y coordinates, we have this cj approximately cj plus 1 minus cj. So the area of this parallelogram can be computed as we have learned in linear algebra. This can be computed as the determinant of a matrix made by these two vectors. So the first row should be this and this. So that is x du x du. I will just omit this argument. So this is just ai plus 1 minus ai, and dy du ai plus 1 minus ai. And the second row is this and this. So dx dv cj plus 1 minus cj, and dy dv cj plus 1 minus cj. Okay, so this determinant is, so this times this minus this times this, and this times this. So that becomes dx du times dy dv. We have this times this and this times this in both terms factors, so we will factorize, and dx d wait a minute, it's u here, ai plus 1 minus ai times cj plus 1 minus cj. Okay, so this is a signed determinant area of the parallelogram. So to make it positive, we take the absolute value. So the area of dij is approximately the absolute value of this. So that is x u dy dv minus, and let's swap this order, x dv and dy du. This is evaluated at this point, ai cj, okay, and ai plus 1 minus ai and cj plus 1 minus cj. By the way, this is the area of eij, as we have seen before here. So let's replace that. So this is mu eij. So the area of dij and the area of eij, they are related by this formula. And this is the absolute value of the Jacobian determinant. So this is equal to the absolute value of the Jacobian at ai cj and mu eij. So if we use the definition, go back to the definition of multiple integral, this is approximated by this. So I from 0 to n minus 1 and j from 0 to n minus 1. And the values of this ai cj ai cj and the area of dij. More parentheses here. And this area is approximately this. So we just replace it. N minus 1 if this cj and Jacobian times mu of eij. But this is the integral of this. Jacobian du dv. So in the limit of infinitely refined partition, then this integral and this integral becomes equal. Okay, let's see a simple example. Let's try to integrate this function, x plus y dx dy, where d is the following region defined by 4 straight lines. Y equals to 1/2 x, y equals to 1/2 x plus 5 over 2, y equals to negative 2x, and y equals to negative 2x plus 5. So D is a region enclosed by these straight lines. So what is this region? Let's visualize it first. So let's see, here's x and here's y. So this line, it's something like this. So y equals to 1/2 x. And this one is parallel to that. Let's see, 1, 2, 3, 4, 5. Let's see. So something like this. So this line and this line, they are parallel. 1 half x plus 5 over 2. And the third line has a negative slope. So this is y equals negative 2x. And the last one is parallel to the third one. So 1, 2, 3, 4, 5. So something like this. Well, actually, this is not a very good figure, but this is supposed to be, these are right angles because this is 1 half and this is negative 2. So they are perpendicular to each other. Anyway, so the region enclosed by these 4 straight lines is this part. Okay. So first, let's try to find those intersections. This is obviously 0, the origin. This is y equals negative 2x plus 5. So let's find this one. So this one is the cross section of this one and this one. So this equals to 2x plus 5. Multiply both sides by 2. We have this 4x plus 10. So adding 4x to both sides, we have 5x equals to 10 and x equals to 2. So y equals to 1 half 2, that's 1. So this point is 2, 1. And this point, this point, this point is, that's, let's see, negative 2x equals to 1 half x plus 5 over 2, multiplying both sides by 2, and moving, adding negative x to both sides. So x is negative 1 and y is negative 2 times negative 1 is 2. So this point is negative 1 and 2. And actually we don't need this point, but let's try to find this one. So this is negative 2x plus 5 equals to 1 over 2x plus 5 over 2. So multiply both sides by 2, 10x, 5. So that's 5 and 5x. So x is 1 and y is negative 2, 1 plus 5, that's 3. So that should be 1 and 3. Actually, this integral can be computed using directly by using iterated integral. So that is, so first we move x from here, negative 1 to 0. And in this range, y can move between this, right? And when x is between 0 and 1, the value of y can move between these two lines. When x is, so this is 1, and when x moves from between 1 and 2, then the value of y can move between this line and this line. So by splitting the integral into 3 parts, we can integrate this function. Anyway, so the integral, if we just directly integrate this is y. this can be so from split into three parts. So this is negative between x is between -1 and 0. Then y is between this line, that's negative 2x, and this line, that is 1 half x plus 5 over 2 x plus y dy first, and dx, and plus x between 0 and 1, and y is between this line and this line. So that's 1 half x and 1 half x plus 5 over 2 and dx, plus x is between 1 and 2. Then y is between this one and this one. So that's 1 half x and negative 2x plus 5 dx. So if you calculate this, you can get the result. But here we try a different way by changing variables. So let's redraw the region D again. So this and this from origin, and that was 2 and 1, and negative 1 and 2. So actually this is a square. Okay, so this is the region D. Okay, let's express this region in different coordinates. So let's take this vector, so that is 2, 1, and this vector, that is negative 1 and 2. And now any point within the region D, inside this region D, can be expressed as actually any point on the two-dimensional plane can be expressed as a linear combination of these two linearly independent vectors. And so x and y can be expressed as a linear combination of these vectors. Let's see, that's u is a scalar, 2, 1, and plus v negative 1, 2. So this is a linear combination of these two vectors. And when the values of u and v are between 0 and 1, then this point is within this region D. Because if u is between 0 and 1, this part, this vector is a scaled vector of this vector, right? So if u is 0, then it's the origin. When u is 1, it's this point, 2 and 1. So between u between 0 and 1, it's somewhere between these 2 points. So somewhere here, okay? And now consider this part. So the scaled vector of this vector is between the origin and this point, negative 1 and 2. So the linear combination of these two is somewhere in this parallelogram that is actually a square. So u is between 0 and 1, and v is also between 0 and 1. Okay, so let's expand this expression. So we have x, y equals to 2u minus v, and y equals to u plus 2v. So let's calculate the Jacobian determinant. So dx du dx dv dy du dy dv. Since these are both linear functions, so it's very easy. So if we differentiate this one with respect to u, we get 2. And differentiate this with respect to v, we have -1. And do the same for y. This is 1 and 2. So the determinant is 2 times 2 minus -1 times 1. So that's 5. So the original integral x plus y dx dy becomes, so this is x, and x is this, so 2u minus v plus u plus 2v, and the Jacobian is 5, that's positive, so just 5, and du dv. And this e in the uv plane is defined by this. So it's just this region between 0 and 1 and between 0 and 1. Okay, so we can convert this into a simple iterated integral. 0 and 1, 0 and 1, so 2u, 1u, that's 3u, plus negative v plus 2v, that's v, d u or whatever, it doesn't matter because the range is the same here. So now we calculate this integral. Oops, don't forget this 5. So 5 is constant, so let's put it here. Okay, so this is 5, 0, 1. So integrate this by u, we have 3 2u squared v u 0, 1 and dv. And 5, and that's 3 over 2 and v 0, 0, 0 here. And integrate this, we have 3 over 2 v 1 over 2 v squared 0 and 1, and that's 3 over 2 1 over 2, that's 0, so that's it. So this plus this is 2, so that's the result is 10. Let's see another example that is nonlinear. So this time, let's integrate this function, x squared, y squared, dx, dy, where d is this region. X non-negative, y non-negative, and x squared plus y squared is less than or equal to a squared. A is a constant. Okay, if you draw the picture of this region, that's this. So x and y. And x non-negative, y non-negative, so we only consider the first quadrant. And this one is x squared plus y squared equals to a squared is a circle. So this is a quarter of a circle with radius a. So the region D is here, this one. Okay, so when something involves x squared plus y squared, it is often helpful if we use the polar coordinate. That is, we transform x and y using the polar coordinate, that is radius and the angle. Y equals to r sine theta. And here r is the distance from the origin, from the origin. Let's see. So let's say this is x and y. This distance from the origin is r, and theta is the angle from the x coordinate. Okay, in this way, this x can be expressed as r times cosine theta. So this is r cosine theta, and the y coordinate is r sine theta. So if we use these polar coordinates, then the range of r and theta are the following. So r can is between 0 and a. Okay, so r is between 0 and a. So and theta can be between 0 and pi half. Theta is between 0 and pi half. So this is a very simple region. So if we draw the picture of this region in r theta plane, then r is between 0 and a, and theta is between 0 and pi half. So it's just this rectangle. Okay, so it's easier to integrate. Next, we need to find the Jacobian determinant of this change of variables. So the Jacobian, let's see, let's have this dx dr dx d theta dy dr dy d theta. So if we differentiate this with respect to r, we have cosine theta. And if we differentiate this, we have negative r sine theta. We do this for y, we have sine theta and r cosine theta. So that is cosine times r cosine, that's r cosine squared, and minus r sine theta times sine theta, that's plus r sine squared theta. So if we factorize, we have r plus cosine squared plus sine squared, that's 1. So this is just r. Okay, so the integral here, x squared y squared dx dy is, let's call this region E. So that's E. So x squared plus y squared, by the way, is just r squared, right? So x squared plus y squared is r squared cosine squared theta r squared sine theta, that is r squared. So here we have r squared, and the Jacobian is r, and dr d theta. Now we use the iterated integral of this. So theta varies from 0 to pi half, and r varies from 0 to a, and we have r cubed here. But this function, by the way, doesn't contain any theta, so we can actually separate two integrals into the product of two integrals. Okay, so that's d theta times this. Okay, so this part is just this, and this part is r to the power 4, and 0 to a, that's pi to a to the power 4, that's pi a to the power 4 over 8. So that's it. Okay, that's all for this video. See you later.